Let us design the flange coupling. This type of flange coupling is unprotective and rigid type. This is the picture of Miss Alfonsa Lona Colangeri. Design the flange coupling, which is unprotective rigid type, to connect the output shaft of an electric motor to the input shaft of a gearbox in a printing machine. The motor delivers a power of 20 kW at a speed of 960 rpm. The starting torque for motor is 15% higher of rated torque. This is how the printing machine looks like. For other design videos, refer to the link provided in the description of this video. Let us look into the design of flange coupling. Power given is 20 into 10 raised to 3 watt and the speed is 960 rpm. In this layout, one can observe that the motor is connected with the gearbox. It is connected with the help of coupling 1, and also the gearbox is connected with the printing machine in the coupling 2. In this question, we are going to design the coupling 1 where the motor is connected to the gearbox. The configurations of coupling 1 and coupling 2 will be quite different, but in the question we are expected to design coupling 1. The first thing that will come into our mind is the difference between protective and unprotective coupling. We can see that with respect to a protective coupling, we have a flange and the flange has some projection. Whereas in unprotective coupling, the flange here has no projection here. The idea is very simple. We know the phenomena of unscrewing of the nut and bolt. While in motion, the unscrewing phenomena takes place and the bolt and the nut can unscrew itself and which may lead to accident. To avoid this accident, this particular projection on the flange is provided. It works like a guard. Hence, this is the difference between protective and unprotective flange coupling. In this question, they have told us to design an unprotective type flange coupling. Now, the second question that comes in your mind is what's the difference between rigid coupling and flexible coupling? There are a lot of differences, but the main difference is about the misalignment. The rigid coupling cannot tolerate any misalignment, whereas the flexible coupling can tolerate 0.5 degree of angular misalignment and 5 mm of axial displacement. Hence, this is the difference between rigid coupling and flexible coupling. In this particular view, you can see the flange with the nuts here. So this is one of the view. In the other view, you can observe that there are bolts that are connected to the flanges. So these are some of the views with respect to the flange coupling. In this figure, one can observe the exploded view of the coupling. In this particular top view, you can observe that there is a recess, and in the figure below, you can observe that in this particular view, there is a spigot. There is a special reason why both of them are placed. You can note that when we assemble both of them, the spigot fits in the recess and the two flanges are located precisely with respect to each other. This ensures alignment of the axis of two shafts. This is necessary because we are designing a rigid coupling and rigid coupling cannot take any type of misalignment. That is, the shaft needs to be exactly collinear. When you go to purchase a coupling, it will look something like this. So this is the actual model when you go and purchase this in the market. Let's study the different parts in the coupling. Now here we have left hand parts and here we have the right hand parts. Let us start with the shaft. Here we have two shafts. One is called as the driver shaft, the other is called as the driven shaft. So there are two shafts which should be collinear. Then this is the key that is mounted on the driver shaft and the key is connected with the hub. You see the hub and the flange is one piece but the shape is little different. So this is the flange of the driver. Now the flange of the driver is connected with the flange of the driven with the help of nut and bolt. So you can see here you have the bolt and you have the nut. So these are the parts involved in the flange coupling. Let us look into the different nomenclatures in the flange coupling. Let us start with D, which is the diameter of the shaft. Capital D is the diameter of the hub. D1 is the pitch circle diameter of the bolt, and D2 is the outer diameter of the flange. We have D1 as the diameter of the bolt, D2 is the diameter of the recess, TF is the thickness of the flange. We have LK, which is the length of the key, and LH, which is the length of the hub. We have discussed in detail and defined this particular nomenclature at this particular point. You can go through it. One can observe the sectional view of the flange coupling. One can clearly see the driver shaft and the driven shaft. The key for the driver shaft and this is the key for the driven shaft. You can see the driver flange and the driven flange. One can observe the diameter here through which the bolts pass through. They have exactly same diameter on the driver flange and driver flange, and you can see no sign of misalignment. So this is the sectional view which gives the idea of how the flange looks from inside. Let us look into the tree diagram where we are going to design the shaft with the torsional shear, design the hub torsional shear. We will design the flange with circumferential shear. We'll design the bolt with the direct shear. We'll design the key with the crushing and the direct shear and some accessory parts. It is given in the question that the starting torque is 1.5 times the rated torque. We can also write it in the way like maximum torque is equal to 1.5 times the minimum torque, or you can also write it as T overall is equal to 1.5 times the T mean. So these are the different ways in which the question can be asked. Let us select the material and the permissible stresses. Let us take the shaft material as C45 and factor of safety to be 5. We know the SYT is 360 Newton per mm square from PSG page number 1.9, and therefore the design tau can be calculated as 36 Newton per mm square. Let us assume that the keys and the bolts are having the same material, that is C30. Let us assume factor of safety to be 5. We know the SYT is 300 Newton per mm square with PSG page number 1.9, and therefore the design crushing stress can be calculated as 72 Newton per mm square, and the design tau can be calculated as 30 Newton per mm square. Let us take the flange material as FG350, that is grey cast iron. Factor of safety can be assumed as 5, and we know from the material itself that the SUT value for FG350 is 350 Newton per mm square. The design tau can be calculated as 35 Newton per mm square. Let us find out the torque. We know power is equal to 2 pi nt by 60. We know the value of power. We know the value of n, that is 960. So the T, which is also the rated torque, can be calculated as 198.94 into 10 raised to 3 Newton mm. We know we have to design with respect to the starting torque. So the starting torque here is 1.5 times multiplied by the rated torque. And when we do so, the starting torque comes as 298.39 10 raised to 3 Newton mm. Let us design the shaft. Torsional shear stress induced in the shaft can be stated by this formula: tau is equal to 16 multiplied by T start upon pi by d cube less than equal to design tau. We know the values here, hence the D can be calculated as 34.81 mm, which can be taken as 35 mm. In the steps of 5 we had to take to accommodate the bearing, hence the diameter of shaft is 35 mm. Let us design the flange. The flange consists of the hub and the flange part. This is the disc. So you can see this part is called as the hub and this part is called as the flange. When both of them are combined, we get this particular figure. Actually, it is one part only, but it has a different shape. So this part of the shape is called as hub and the disc part is called as the flange. Design of the hub. The length of the hub is given as LH. LH is 1.5 times D, which comes around 53 mm. The outer diameter of the hub is given by capital D. Capital D is 2 into small d, that is the diameter of the shaft, which comes around 70 mm. The hub is treated as a hollow shaft subjected to a torsional moment. The maximum torsion stress is given as 16 multiplied by T into dO upon pi dO raised to 4 minus di raised to 4. So this is a formula which is given in PhD 7.21. So here dO is capital D and di is small d in our case. So we'll modify the formula accordingly. After putting the known values into the equation, we can see that the induced torsional shear stress is 4.72, which is quite less than the design torsional shear. Hence, the hub is safe against shear failure. Let us design the flange. The thickness of the flange is given by TF. TF is 0.5 times D. When we put in the known values, TF comes around 18 mm. Now, outer diameter of the flange is given by D2. D2 is 4 multiplied by D, that is the diameter of the shaft. So D2 value we get around 140 mm. The flange is subjected to circumferential shear stress. We know the formula: induced tau is equal to T start upon D by 2 upon pi d Tf. Here in the figure one can observe that this hub is connected with the flange rigidly, but due to the torsional what will happen is this particular section which is marked in red will get sheared off, and this particular shear is circumferential stress, and circumferential area will be considered, that is pi into d into Tf. We will substitute the known values into the circumferential shear stress, and the induced shear stress comes around 2.15, which is quite less with respect to the design shear stress. Hence the flange is safe. Let us assume some data with respect to flange. The clearance between the spigot and the recess is indicated by A, which is assumed as 5 mm. The projection of the spigot, which is given by B, capital B, is 5 mm. That is also assumed. So the total distance C is A plus B. In the figure you can observe the C distance. The recess diameter of the flange is given by D2, and D2 is 1.5 times D. So we have taken this empirical relation. After substituting the known values, the D2 comes around 52.5 mm. Let us design the bolt. Here diameter is 35 mm. We know that. Pitch circle diameter of the bolt is given by D1. Here D1 is equal to 3D. After substituting the values, D1 comes around 105 mm. The number of bolts with respect to the flange. N is 3 when the diameter is less than 40 mm. N is equal to 4 when the diameter of the shaft is in between 40 mm to 100 mm. And N is equal to 6 when the diameter of the shaft is between 100 and 180 mm. So in our case, N is equal to 3 because the diameter of the shaft is less than 40 mm, that is 35 mm. The direct shear stress acting on the bolt can be written in this manner. Induced tau is equal to T start upon D1 upon 2 upon N multiplied by pi by 4 DC square, where DC is the core diameter of the bolt and this is the design tau. After substituting the known values, DC comes around 8.18 mm. We can select a standard bolt from PSG 5.42. A standard bolt is M10 with the pitch 1.5 mm. This is an isometric screw thread bolt. Design of the key. Let us assume the parallel key from PSG page number 5.16. For a shaft diameter between 30 to 38 mm, The width can be taken as 10 mm and height can be taken as 8 mm. Length of the key can be taken as LH plus 5, where LH is the length of the hub. We know the length of the hub is 1.5 times D plus 5. After substituting the values, the length of the key is equal to 58 mm. Let us consider the crushing stress induced in the key due to shaft. In this figure, one can observe that we have the shaft, the key and the flange. Half of the key is within the shaft and half of the key is within the flange. The key which is in contact with the shaft experiences a crushing stress as shown in this red color. The induced crushing stress can be written as T start upon D by 2 upon H by 2 into Lk. You can observe that the height where the crushing stress is induced is H by 2 and the length is Lk. Hence this becomes the area. The shaded area is the crushing area. You can simplify the equation in the following manner. After substituting the known values into the equation, the length of the key comes around 60 mm. Hence, the length of the key with respect to the crushing stress is equal to 60 mm. Let us understand the direct shear stress induced in the key due to shaft. So one can observe the shaft and the key, and half of the key is within the shaft and half of the key is within the flange. Due to the direct shear stress, the red color thing is the area, shear area, which gets sheared off. So this area is under consideration. We can write the formula of the induced shear stress as T start upon D by 2 upon B into Lk, where B is the width and Lk is the length of the key. Hence we can substitute the known values into the equation and the length of the key can be calculated as 57 mm. Hence we get length of the key as 57 mm with respect to shear stress. Now we'll find out the length which we have got due to empirical relation, due to crushing stress, due to shear stress and select the higher value. Hence the final value of the length of the key is 60 mm. At this point we can conclude the design.